Hi viewers, this is Dr. Jana and you are watching video with me on support vector machine. Support vector machine is a classification algorithm. We already seen two videos regarding the regression and classification. With classification, we predict the categories, while in regression, we generally predict the values. And this support vector machine, it is a type of classification algorithm that classifies data based on its features. Whatever the features we are giving in x-axis, x1, x2, x3, there are different features, and SVM will classify any new element into one of these two categories. For example, our input is given a number of fruits. You can see it here. One can be orange, one can be apple, like that it is given. So red color it is given the apples, and you can see the orange color it is given there. Then this input we pass to a machine using our machine learning some algorithm and all things. Okay, this try to segregate and classify the data. So classifying data, it is classifying similar type of red color to one category, one classification, and this orange into one. Then when we put a new input to this one, then based on this classification and verification, then it classify, because now what I have given, unknown fruit I have given it here. This unknown fruit, based on this algorithm, it classified into one of the group, because it classified into two groups. One is the apple and another is the orange. So this new one, based on this algorithm, it will put to a category. So this is the mechanism how it works in our support vector machine. Right now, let us go to in details about the support vector machine. In support vector machine, if you see, once we give some inputs, the algorithm will segregate and classify the data and then create the outputs. This is the things what you have seen in the pictures. When you give a new data or unknown fruit variable, in this example, the algorithm will correctly classify that is the fruit is apple, or so apple or orange, whatever things, based on that it will classify. So this support vector machine, we are having two types of support vector machines, and each used for different things. One is the simple support vector machine, typically used for linear regressions and classification problem. Then another one is the kernel support vector machine. It has more flexibility for nonlinear data, because we can add more features to fit a hyperplane instead of just two-dimensional space. Okay, so this hyperplane, because in a two-dimensional it is separating by lines, in the three dimensions we are calling it the hyperplane. All the things we'll study in details. Fine. So this is the things what happens inside this support vector machine. Right now we are moving to our next thing. Here we see in supervised learning, the classification is multidimensional in the sense that sometimes we have two classes like yes or no, true or false. But sometimes we have more than two. For instance, suppose you are going for the risk modeling. Under risk modeling, we can have low risk, we can have medium risk, we can have high risk. So here it is not two classes. Yeah, it is more than two classes. But the support vector machine, it is a binary classifier. A classifier used for those true or false, yes no type of classification problem. Here the features are important in supervised learning. If there are several features, SVM may be the better. Okay, for less data, when the features are more, in those cases the support vector machines will be better classification algorithm choice as opposed to the logistic regression. So this is the thing that is the reason why we prefer this support vector machine, where the data set is less but the number of features are more. Right. So then coming to the next one, we'll come here. In this slide, we'll see how the data is divided and what we do it here. Technically, this dividing line is called a hyperplane. Say for separating it to one category and another category, this dividing the line we call it as a hyperplane. In two-dimensional spaces, we typically refer to the dividing lines as lines, but in three dimensions and higher dimensions, they are considered as planes, or we call it as the hyperplanes. The hyperplane with a maximum distance from the support vectors, I'll tell you what are the support vector and how it works. So the maximum distance between the support vector is one we want here, and sometimes it is called the positive hyperplane d plus, and it is the shortest distance from a support vector. If the line the minimum distance we call it as the d minus, and the positive hyperplane the maximum distance we call it as the positive hyperplane, or the this is also called the negative hyperplane, and the sum of for d plus and d minus, it is called the distance margin. Okay, so this distance we call it as the margin, and we should always try to maximize the distance margin to avoid the misclassification. Okay, the main thing in our hyperplane, we have to maximize this margin. Okay, when the classification is only between two classes, it is called a linear support vector machine, right? So in case of kernel support vector machine, classification problem with higher dimension data, this is the things already we discussed, and we have some idea about that one. So if there is no linear classification or linear separations between the two classes, they are not linearly separable, that we know. So that means if you are unable to separate by a line, so this belong to one class, other, then it is not linearly separable. Then what we need? We need to transform it into higher dimensions by employing a kernel function to the data set. So this is the idea how we go for non-linear, that means which cannot be separated by a line. Those type of cases, just we are using a kernel function. Using these kernel functions, we can go for those things, right? So how this kernel function it works, now to learn. Before that, let us see some example how exactly the linear classification in SVM does, and how what it does. You can see it here. Here in the left hand side, you can see this diagram. We are having a 2D separation line. Here, this is divided by a linear line into two different categories or two different classes. You can see below this line it is one class, and above this it is another classes. And but where if you see from a through 2D pictures, so these green and red lines are interlaced or they are mixed. So in that case, it will be difficult for you to separate it by a line. Then what we do? We use a kernel functions, and these kernel functions will convert a two-dimensional space to a three-dimensional space, and once the data is separated into three dimensions, then we can apply the support vector machines and separate the two groups using the two-dimensional plane. So this is the things it happens. In case of 3D, if there is 3D plus, there is also another way, just like that hyperbolic curve and all things in a three dimension we can see. That I am not covering it here. It is who are interested for higher study, they can go for that one. They can follow some reference. Okay, so we are focusing on these 2D and also 3D separations occurring in a plane, right? So then we are moving to the next one. Then in our slide number 6, we will come across some other things like now, while we are going for this nonlinear support vector machine, then what the different type of kernel functions we will be using, and we are having mainly three type of these kernel functions. One is the Gaussian radial basis functions kernel, second one is the sigmoid kernel, third one is the polynomial kernel. Okay, so depending on the dimensions and how we want to transform the data, we can choose from any of these kernel functions. You understand? So it is clear when you are going for the linear SVM, this is not required, just you separate and you can do it here. And how you do in linear also, that we will discuss in detail. Just we are giving the fundamentals. In case of linear, what we do, and in case of non-linear, we use some kernel functions, and these are the possible type of kernel functions where using any of these kernel functions we can transform it and we can go for separating it, right? So these are the things. Then we go for this slide number 7, and here another important and interesting thing you will see in 7. The SVMs are used in applications like handwriting recognitions, the intrusion detection, face detection, email classification, gene classification, and in web pages also we are using these support vector machines. And this is one of the reasons we use the support vector machines in machine learning, and it can handle both classification and regression on linear and non-linear data. That is the important things why you are going for these support vector machines, right? And another reason that we use SVMs because they can find complex relationships between our data without we need to do a lot of transformations in our own data. Okay, so it is a great option when you are looking with similar data sets that have tens of hundreds and thousands of features, because the data set is less, but the number of features are more. In that case, I told you that this SVM is more suitable, and they typically find more accurate results when compared to other algorithms like the logistic regression and other things. Go for that. Okay, so these are the regions or conditions where we use this SVM. Okay, then we are moving to our slide number 8. In the slide number 8, we can see it here. Yeah. Now let us have a detailed discussion about these things what you are using. This kernel functions what you are using, the linear kernel functions we are using. These are commonly recommended for text classifications. What we call it, the linear kernel function is there, the other is there. I told you the Gaussian is there. I am using the RBFN, and we are having other things. First, we are going for this linear, right? The linear kernel function. These are commonly recommended for text classifications because most of these type of classifications problems are linearly separable. For that, what do we do? Fx which is equal to w to the power 2 into x plus b. Okay, so b is a linear coefficient, we know, and x is the data that we are going to classify. Okay, so using this we try to find a function fx, and using that one we are able to set a boundary, decision boundary, that it will be able to separate all these things. Okay, so this is the number 1 type of kernel. So if you see here, it is similar to y is equal to fx plus c, similar to some or more or less. It is because it is a linear, it is able to. Then the polynomial kernel functions, practically it is not used. Why? Because it is not as computational efficient as other kernels, and the predictions are not accurate. Because of these things we are not using, but you should have some idea. Here we are using function of x1 and x2. x1 and x2 are the features given in the x-axis. So which is equal to a plus x1 to the power t into x2 to the power b. Okay, so b already I told you, this is a linear coefficient, and x1 and x2 represent the data. Okay, so using all the things, we can also apply these polynomial kernel functions, but remember that practically we are not using this polynomial kernel functions, right? So these two, it is only for information purpose I am giving you, and the most used things we will be discussing right now. Okay. Now we are moving to the support vector machine, the next slide, where we can clearly see the Gaussian radial function, RBFN, Gaussian radial basis function, or the RBFFs, and it is one of the most powerful and commonly used kernels in support vector machines. Usually the choice for a nonlinear data, we can go for this Gaussian radial basis function or RBF. Okay, how do we put it here? Here function of x1 comma x2, x1 x2 the data we have given, which is equal to e to the power minus gamma into mod of x1 minus x2 to the power 2. Okay, x1 minus x2 irrespective of the sign convention, just you put the power 2, right? So in this equation, gamma specifies how much a single training point has on the other data points around it. Then this mod of x1 minus x2 is the dot product between our feature sigmoid, and more useful in these are the things we are using, the Gaussian radial functions most frequently using. And another type is the sigmoid function, and it is more useful in neural networks than the support vector machines, but sometimes also occasionally we can also use all the things, right? So here function of xy, there you see previously we are using function of x1 x2, here function of xy is equal to hyperbolic function tan h of alpha into x to the power t into y plus c. So in this function, alpha is a weight vector and c is the offset value, that is account for this some misclassification of the data. What happens? Okay, so these are the things. So you remember that out of these four, most frequently we will be using this Gaussian radial basis function, or some cases we may go for this sigmoid. But these sigmoid functions, what you are using it here, it is usually used in the networking, okay, neural network and all things, but sometimes we can use it here also for this purpose, right? Now moving to the last type of kernel functions we are using, you have it. What are the precautions or what are the importance you have to see while you are going for this support vector machines? First of all, our data should be numeric. instead of categorical. If it is categorical, you have to convert to numerical. For example, gender, it is given male, female, so you can write male as 1 and female as 0. So it is to be converted to some numeric, okay, because SVMs expect numbers instead of other kinds of labels. So labeling data it cannot do, right? Then we can remove the duplicate data, because sometimes while you copy the data there will be a number of duplications possibilities there. So you have to remove the duplications. Using this, our Python, we can easily remove all the duplications. Then we convert all data to ranges, that is 0 to 1 or minus 1 to 1. Okay, instead of high values you can convert to a range between this. Then check kernel cache size as it affects the RAM. So you are taking so many features, 1000, 2000. So the processing, it takes a lot of time. So huge amount of RAM is also required. So those are the things you have to remember or keep in your mind while you are going for using this support vector machines, right? Then let us have an idea, because till now we are talking about domain theory. What happens actually and how we work on these things. You see, in the slide number 11 you can see, first of all we have plotted all our data. So we have plotted some data, red bulb or blue bulb, all we have plotted it here. After this plotting of this data, it is just first initially whatever the data we got, that we try to plot it and visualize how it looks. Then we try to find a line, and by this line there can be a number of lines in between, because if I try to draw a boundary here between these two, so a line from this point to this point is possible, a line from this point to this point is possible, this point, all things are possible. Now even if a line here also it is possible. So the thing is that how do you decide which is the best line? Okay, there must be certain rules and regulations. So this thing, what we do, suppose we draw a line here, the center line you can see it here, L2 is the line I draw it here. Then the data points who are close to that one, we call it as the support vector. If you see where I am putting my cursor here, this is one support vector, this is another support vector, this is a support vector, this is also another support vector. So initially I have taken the line 2, say let it be. In this line 2, from this point I draw the distance of this one. Then all the three lines I have taken. From this point what is the distance, from this point what is the distance, and from this point what is the distance. Okay, so out of these three lines, who are more close to the data point in the blue. Okay, so you can see this is more close to that one, that is line number I can say 1. Similarly, out of these three, which line is more close to the support vector of red? Okay, something I find that this line is more close to that one. You get it now? Now the distance between these support vectors, the distance between this support vector, if you draw a line, draw a plane, we call it as a hyperplane, or the initially for the 2 dimension we call it a line. And the distance, the distance between the vectors, what you draw the line, so this we call it as the margin. And this margin, what are you telling, that it should be maximum. If the margin is maximum, the margin distance, the distance between L1 and L3, it becomes a margin, or you can draw another line which is more close to that one. So like that we can find the distance and we can go for the margin. So in this way, maximum the margin, the better is the hyperplane, and it is more easily will be able to classify the data. Fine. So this is the slide number 11. I think we can go for the slide number 12. Fine. Now let us see, in this slide support vector machine, if you minutely observe, we now come to some overview of all the things. We have linear SVM, we have non-linear SVM or support vector machines. In case of linear separation line, and there is infinite number of line exist, and SVM try to find the optimum or optimal line. And once you find the optimal line, then it classifies the classes with this maximum margin. Margin I told you, that is the distance between the support vectors of different classes and categories. So this maximum margin, with that we decide a hyperplane, and with that we will be able to separate. That is the cases in case of our linear support vector machines. While you are coming to the non-linear support vector machine, it uses the soft margin and also a kernel trick sometimes. Okay. So soft margin, what is the, because kernel trick will discuss, because we are using the kernel functions, but what is the soft margin? The hyperplanes, separate the class. We know one class from blue to red it separates, and data points close to the line it is called the support vector. That also I already explained. And using the support vector we are able to find the separating the two classes, and we call the line as hyperplane, and hyperplane can be of many, and we need to find the best hyperplane. So out of that, which is the best, we have to find it that, because based on what we decide, based on this margin. And the distance between support vector shall be maximum, and it is called the margin, and hyperplane has maximum margin. These are the points you have to remember. And sometimes we go for tolerating or accepting some misclassifications. What is the meaning of that one? Suppose while you are making a plane and one of the data points is inside that plane, so in that case it will be difficult for us to draw a line. So in that case we can also tolerate the misclassifications, because while you are classifying or while you are training, we can do mistake and we can also learn from that one. How many like that misclassification we tolerate? We call it as the regularizations. You get it now? So sometimes we tolerate or accept the misclassification. So like that, how many misclassification we tolerate, we call it as the regularizations. This regularization is denoted by C. This we call it as the degree of tolerance. What is the regularization? This is the degree of tolerance. So there is a rule: lower the C, the margin will be high, and higher the C, the margin will be low. Then what do we want? I want the margin will be high. If I want the margin should be high, then C must be low. What is C? C is just our what I told you, the regularizations, right? Now what we do? Convert the non-linearly separable to a separable using a soft margin. I told you what is the soft margin, and fit a line that makes mistakes during the training itself, and soft margin during the training tolerates misclassification. So these are the things we keep in our mind while you are going for this support vector machine. Now we are moving to the slide number 13, where we will see again. Let us see. Now we go for some coding. From this coding you can understand what happens and how do you go for that one. Suppose I am going for a linear classifications. What do you do? So I am using some of the MATLAB libraries, like the import matplotlib pyplot as plt, import numpy as np, import sklearn, import svm, okay, and some linear data. It's a x is equal to np.array. So this is the data set I have taken it there, and y is equal to something I have taken it there. Then plot x between y, and I am using the plot.scatter and plot.show. Once I go for the plot.show, you can see all the points are scattered here. Can you see it here? So this is the thing which happened in our SVM, that is the linear regressions, right? Okay, then we moving to the number 14, slide number 14. Yeah, here then how you go for the classification? Let us see. Here what we do? Yeah, just it is opening, and yeah, you will be comfortable here. Now shifting the data to training the models. Now suppose we divide into training of x np dot vstack xy dot t, and training of y, we did it like this. Then defining the model, CLF is the model, svm dot svc, kernel we are using a linear, because it is just it is a linear data type of data, so linear regression type of thing, so we are using linear, and c is equal to 1.0. What is the c here? C, the regularization, what I have told you that, right? So now train the method clf.fit, because it has to fit the best fit, train x and train y, then getting the weight value for the linear equation from this training of this SVM model. So this w is equal to clf.coefficient of 0. Now we can get the y offset of the linear equations. We get it a is equal to minus w of 0 by w of 1. Then make the x-axis space for the data points. X-axis is equal to np line space 0 to 13. So you can see it here, it is given x-axis 0 to 13 here, y it is given all the things it is plotted here, it is between 0 to 10 or 12 it is given right there, right? Now the plot the decision boundary, plt dot plot xs, y and k. Okay, based on this k it has to go for that one. Now you see, if you see here, some blue dots are here in the bottom and some yellow dots are there in the top, and we are able to have a line separating both the things, right? So now show the plot visually, and the plot dot plt dot show, plt dot legend, some legend also you can put it at what are the things you want to show. You can show, I have not put any legend, so you can write it there. Okay, plt dot show, you can show. Now we are able to classify, we are able to classify a linear SVM support vector machine using the linear SVM. The next slide, slide number 15, will be going for this non-linear, okay, SVM 15. Now, how we go for this non-linear SVM? This is just the example. You can have real-time data and all things. It is only for explanations. I am putting all things. If you are able to say, I do not know, yeah, I think initially you can see. In this non-linear SVM example, we use the same thing. Import matplotlib, so as PLT, import numpy as NP, sklearn and data sets, and from sklearn import SVM support vector machine we are using. Then because non-linear I am using circle X, circle Y, and the data sets make circles. So all the things I am putting here. I am putting some noise is equal to 0.05 also. Then I am plotting it, plt.scatter, all the things I am plotting, and all the things, and plt show. If you plot this one, you can see the right hand side, the figure you can see it here, and you are able to plot it now. Now make nonlinear algorithm for a model, formatting nonlinear underscore CLF, which is SVM underscore SVM.SBC kernel. You are using RBF function, and C is equal to 1 also I am using. Okay, then I made it a model. Now nonlinear CLF.fit. So now for training, I am using the .fit circle X and circle Y, whatever the data we already decided. Now plot the decision boundaries. That is using the define plot decision boundary model X is equal to none, as X is equal to none, X is equal to plot. So you see, if you run this one, then X linear and Y linear, all the things are given it there, and create a grid to evaluate model. For that X, Y and Y, X both we have to put it here, and for shaping the data X, Y, all it is given it here. For plotting the data, plot scatter, and also all things. Now if you run this program after all the things and finally plot, so can you see here, can you see it here? So it is able to separate the data. It is, I cannot say it is a linear function, but non-linear things, it is able to, just in a oval shape, it has segregated all the yellow points are there inside, and all the blue points are there outside this line. Okay, so this is all about some idea about all these software vector machines. And if you more interested for the execution part, most probably I will try to cover in our next slide, because we are initially going for all these theories, and once all the things are completed, we will be going for this execution using this Python. And thank you for watching this video and attending this class. If you really like this video, please do share with your friends. If you have doubt or any queries, don't hesitate to send it through SMS or through chat. Even if my number is there also, you can forward to me. Thank you once again. Have a good day. Take care of your health.